Okay, let's continue. Inverses. Let's begin. Can we define additive inverse of a rational? So, definition. Additive inverse. Let A be a rational. The unique rational box such that A plus box is 0 is called the additive inverse of A. So, the additive inverse of A is the unique rational box such that it kind of undoes A with respect to addition. A plus box equals 0. So, we have defined additive inverse. We can ask, does every rational have an additive inverse? So, observation. Let A be a rational. Then A has an additive inverse. So let's show that every rational has an additive inverse. So let A be m by n, where mn are integers and n is not equal to 0. First we need to show the existence of a box such that A plus box equals 0. So consider minus m by n. We have m by n plus minus m by n equals 0. Hence, m by n plus box equals 0 for box equals minus m by n. So there is some rational box such that when you add box to m by n, you get 0. So we showed existence. Now we need to show uniqueness. Say m by n plus box equals 0 for some rational box. Adding minus m by n both sides, we have box equals minus m by n. So we showed that if m by n plus box equals 0 for some rational box, then that rational box should be minus m by n. So this shows uniqueness. From 1 and 2, we see minus m by n is the unique rational box such that m by n plus box equals 0. Hence, we have shown that hence A equals m by n has an additive inverse. has an additive inverse which is minus m by n. Okay, so we'll discuss some notation. Let A be a rational. The above additive inverse of A so we showed that let A be a rational, then A has an additive inverse. So we showed that every rational has an additive inverse. Now consider this notation. Let A be a rational. The additive inverse of A is written as minus A. If A equals m by n, where m and n are integers and n is not equal to 0, we have the additive inverse of A equals minus m by n. So we showed that every rational m by n has an additive inverse, and that additive inverse is minus m by n. Okay. Now we can ask, can we similarly define multiplicative inverse of a rational? So just to recap, what did we do? We first defined additive inverse of a rational. Additive inverse of a rational A is the unique rational box such that A plus box equals 0. Then we showed that every rational has an additive inverse, and that additive inverse is of this specific form. If A is of the form m by n, then the additive inverse is of the form minus m by n. Now we'll do a similar thing for multiplicative inverses. Can we define multiplicative inverse of a rational? Multiplicative inverse. Let A be a rational. The unique rational box such that A times box equals 1 is naturally called the multiplicative inverse of A. The multiplicative inverse of A, right? Now we can ask, does every non-zero rational, so 0, the rational number 0 doesn't have a multiplicative inverse. Does every non-zero rational have a multiplicative inverse? So we have an observation. So by the way, 0 doesn't have a multiplicative inverse because 0 times box equals 0 for any rational box. So it can never equals 1. So 0 times box can never equal 1, whatever rational box you pick. Hence 0 has no multiplicative inverse. Now, does every non-zero rational have a multiplicative inverse? Turns out like with additive inverses, every non-zero rational, just that you need to add non-zero rational. Every non-zero rational has a multiplicative inverse. Let A be a rational, A not equal to 0. Then A has a multiplicative inverse. right? So the proof, let A be of the form m by n, where mn are integers and A is non-zero. Hence we can take m not equal to 0 and n not equal to 0, right? Now for existence, consider n by m. We have m by n times n by n equals mn by nm equals 1. Hence m by n times box equals 1 for box equals n by m, right? Now we show uniqueness, that n by m is the unique rational box such that m by n times box is 1. Now for uniqueness, say m by n times box equals 1 for some rational box. Multiplying n by m both sides, we see box equals n by m. Now from 1 and 2, so 1 shows that m by n times box equals 1 for box equals n by m. So there is some rational box for which m by n times box equals 1. We found a rational, so the existence is guaranteed. Now we need to show uniqueness. Here we define multiplicative inverse to be the unique rational box such that A times box is 1. So we need to show that there is a unique rational box such that m by n times box equals 1. Now suppose m by n times box equals 1 for some rational box. Then we can deduce that that rational box must be n by m. Hence from 1 and 2, we see n by m is the unique rational. Box such that m by n times box equals 1. Hence, how did we write here? Hence A equals m by n not equal to 0 has a multiplicative inverse which is n by m. So we showed that every non-zero rational has a multiplicative inverse. So let A be a rational, A not equal to 0. The multiplicative inverse of A. We showed that the multiplicative inverse of A exists. The multiplicative inverse of A is written as A inverse A raised to minus 1. We saw that if A equals m by n, mn integers, and A is non-zero, so m is non-zero and n is anyways non-zero, we have A inverse equals n by m. Hence we have found the additive inverse. We have found that the additive inverse of a rational m by n is minus m by n, and we have found that the multiplicative inverse of a rational m by n, which is non-zero, is n by m. So we found additive inverse of a rational, of any rational, and multiplicative inverse of any non-zero rational. Right. Now we can ask another question. We have defined additive inverses and multiplicative inverses. Can we define ratio of rationals? We can ask this. Can we define A by B for rationals AB with B not equal to 0? So we define ratio of rationals let A be rationals, B not equal to 0. The unique rational box such that B times box equals A is called A by B. So we have defined ratio of two rationals. Let A, B be rationals, B not equal to 0. The unique rational box such that B times box is A is called the rational A by B. So here we have defined ratio of rationals. Does A by B exist for every rational A B with A not with B not equal to 0? Does A by B exist for every rational A B with B not equal to 0? So observation. Ratio of rationals let A B be rationals, B not equal to 0. Then A by B exists and the A by B is in fact the multiplicative inverse of B times A. So the proof is as usual. We first show existence. So consider B inverse A. Now B times B inverse A equals 1 times A equals A. Hence B times box equals A for box equals B inverse A. Next we show uniqueness. Say B times box equals A for some rational box. Multiplying by the multiplicative inverse of B both sides, we have box equals B inverse A. So we showed that B times box equals A for the rational box equals B inverse A. We also showed that if B times box equals A for some rational box, then that rational box must be B inverse A. From 1 and 2, we see B inverse A is the unique rational box such that B times box equals A. Hence A by B exists and is A by B equals B inverse A. So we have defined additive inverse, multiplicative inverse, and ratio of rationals. So we have found that the additive inverse of a rational m by n is minus m by n. The multiplicative inverse of a non-zero rational m by n is n by m. This equation, A inverse is n by n. Minus A is minus m by n. A inverse is n by m. And for two rationals A and B, where B is not equal to 0, the symbol A by B, we have defined it to be the unique rational such that B times that rational is A, and this unique rational always exists when B is not equal to 0, and that in this unique rational is B inverse times A. A by B is B inverse, the multiplicative inverse of B times A. So we have defined additive inverse minus additive inverse, multiplicative inverse, and ratio of two rational numbers. So that's all for this part. See you in the next part.